Hi, we're the team from National Chung Kung University. Today, I'll be presenting our work on AAMLA, a framework for predicting student collaboration satisfaction in game-based learning using multimodal behavioral signals. So what's the setting? In collaborative game-based learning, small groups of students work together inside a virtual environment to solve real-world problems. Think of it as a classroom, but the classroom is a game, and every student action leaves a trace we can analyze. One signal we care about is collaboration satisfaction, which reflects how students feel about the quality of their group experience. It's strongly linked to engagement and learning outcomes. The question is, can we predict it automatically, without waiting for students to fill out a survey after class? That timing matters. Post hoc surveys tell you what happened, but they don't help you act on it. Automatic prediction gives instructors a real-time signal, so they can step in while the collaboration is still happening and actually make a difference. To build that prediction, we use 4 behavioral modalities captured during gameplay. Facial action units for emotional state, head pose for attentiveness, eye gaze for visual attention, and trace logs which record every chat message, NPC interaction, and piece of evidence collected in the game. Each modality captures something different, and together they give us a much richer picture than any single signal alone. A prior approach from the Educational Data Mining Conference in 2024 tackled this using cross-attention fusion across these 4 modalities. It set a strong baseline, but it relies on one assumption that turns out to be fragile: that all modalities are equally informative at all times. In practice, that assumption breaks. Gaze features are noisy. They vary across students, lighting conditions, and camera angles. When cross-attention assigns high weight to a degraded gaze signal, that noise doesn't stay local. It propagates through the entire fusion pipeline, corrupting the final representation and producing wrong predictions. That's the cascading error problem. But the answer isn't to just drop gaze entirely. That modality might still carry useful signal for other students or in other contexts. What we need is a way to suppress unreliable modalities adaptively, down-weighting them when they're noisy without permanently discarding them. That's exactly what our framework does. AAMLA uses a module called CAMA, which stands for Cross-modal Affinity-Guided Modality Alignment, to explicitly model and manage intermodal relationships during training. CAMA starts with a stabilization step. During training, each sample is processed twice, once clean and once with simulated degradation. The 2 embeddings are averaged before anything else happens. This means even a heavily degraded gaze embedding gets mixed with its cleaner version before it influences the affinity computation. A single bad frame can't corrupt the whole batch. This is the core reason AAMLA remains stable even at 70% gaze dropout. On top of that, we introduce an affinity-driven contrastive loss. We compute a cross-modal affinity matrix, then apply 2 constraints. Same student activity embeddings across different modalities should have high affinity, so they're pulled together. Different student activity embeddings should have low affinity, so they're pushed apart. Gaze, which has naturally low affinity, receives the largest corrective gradient. Over training, CAMA learns to downweight it automatically with no manual rules needed. The TSNE plots show what each component is doing. With the full model, the 4 satisfaction classes form tight, well-separated clusters. Remove CAMA and you get cross-modality drift. Remove the affinity loss and the class boundaries fragment. Remove both and all structure collapses. CAMA and the affinity loss play distinct roles. One aligns, the other discriminates. You need both. The numbers back this up. AAMLA reaches an F1 score of 0.79, compared to 0.72 for cross-attention and 0.66 for the best unimodal model. But the robustness numbers are the real story. At 70% gaze dropout, cross-attention drops to 0.52. AAMLA holds at 0.72. Even when an entire modality is removed at inference, AAMLA's worst case is 0.68, well above cross-attention under similar conditions. 2 more findings. Full multimodal gives the best performance, but trace plus AU plus pose reaches an F1 of 0.74 even without gaze, showing the framework degrades gracefully. And SHAP analysis confirms that trace features dominate: chat frequency, NPC interactions, and evidence collection. Gaze doesn't appear in the top 20 features at all, which directly validates that CAMA suppression is working as intended. To wrap up, AAMLA is designed for real deployment conditions, where sensors fail and data is messy. CAMA learns which modalities to trust, rather than assuming they're all equally reliable. Explicit alignment isn't a nice-to-have in educational settings. It's a practical necessity because modality degradation is the norm, not the exception. That's all from me. Thank you for listening.